Just a moment, please. Okay, I think we are live now. So yeah, I'm in the camera. Okay, so hello everyone. Welcome to the Tuesday seminar at the University of Warsaw Astronomical Observatory. And today we are continuing our journey across the solar system. But today we're going to have a special guest who's a geologist, never had a geologist. I remember. So, who's going to tell us about craters and what happens when an asteroid hits the Earth. Anya, please.
Hi. Thank you very much for coming to my geological presentation. I hope that I managed to properly adjust the, the level of geological information that will be at the same time interesting for you and understandable, because I'm aware that it's a slightly different way of thinking on asteroids and what is happening to them. So today I'm going to tell you what is happening when an asteroid, so something that you are very familiar with, is meeting our own planet. What are the effects and what can we study related to that? Come on. Okay, so as you know, the impact cratering is actually the most important recent geological process that is happening all over the solar system. Obviously, there's plenty of impact craters on the moon, for example, and there are new being formed all the time. So, for example, this is like lunar flash, which is when an asteroid, sizable asteroids, is hitting the surface of the moon, and sometimes it's even large enough and well observed enough to match the lunar flash with the crater that have been formed. So, for example, this one have been formed on the 17th of March, 2013, and the crater was 18 meters. Thanks to numerous observations.
Excuse me for a moment.
Yes?
Excuse me, I need to switch the Wi-Fi because it's horrible.
Please let me know when should I start and if should I start from the very beginning. In the meantime, I can do some hand dancing.
You're back now. Okay.
Perfect. Is it better now?
Yeah, it should be better. Thank you. Sorry.
Okay, great. So those kind of collisions are happening all the time. And for example, if we are able to match the lunar flash, which are, it's a phenomenon, as I'm sure, more aware of it than I am. It's pretty common phenomenon. If you look closely enough with the impact crater, you can also look back in time and figure out how large was the impactor that produced all the craters that you can see on this image, and calculate the impact rate in the past as well. So obviously, the impact craters are also visible on all other planets or stiff planets and moons all over the solar system, and most probably also beyond. However, the amount of material that is hitting the Earth atmosphere is actually, reasonably large if you think about that, because it's about 100 tons per day. The estimations differ by quite a lot, but this is like a middle ground, which is equal to a whale, the great blue whale, being just splashed over the entire Earth every day. So, it's not insignificant amount of material. However, most of it is in the form of very, very small grains that if we are lucky, are only visible as shooting stars. However, from time to time, those bodies are larger. So, for example, we all remember the event that took place in 2013, when an asteroid that was about 20 meters in diameter exploded over the city in Russia, Chelyabinsk. And more than 1,000 people were seriously injured. However, no impact craters have been found in relation to this event. So this is not what I'm studying. I'm not interested in those smaller ones or less tough ones that explode in the atmosphere without leaving any traces, because exactly that. If for geological investigation of an effect of such a body, we need something that survives long enough for us to find and study. So currently on Earth, we know only about 200 of places where we are sure that an asteroid hit the Earth and created an impact crater. There was definitely much more of those kind of events in the past. If when you compare for example, we just look at the surface of the moon, we can be assured about that. However, due to a very active geology of Earth, the rocks are constantly being recycled. So only in specific places those signs of impacts, past cosmic impacts, can survive. And this is why, for example, in Europe, if you look, there is plenty of impact craters in the northern part of Europe, but there are very few in the southern part of Europe. This is mostly related to the fact that the average age of rocks in Scandinavia is much higher than in the south. So those rocks had much more time to kind of accumulate the rocks. Second thing is also that for example, if we look at the surface of Africa, we can see that there is quite a lot of impact craters here in this yellow part, and also here in this yellow part, but very few in this green part here. Even though on average, more or less, entire Africa is pretty old. The rocks are very old, so had more or less equal time to accumulate all the impact craters. So there's also another issue that is controlling the distribution and distribution of known impact craters, which is how easy is it to see them. So very often the first step in finding an impact crater is to look through especially the larger ones, is to look, smaller ones as well. Anyway, is to look at the satellite images, and obviously it's much easier to see beautiful rocks with beautiful impact craters if they are not covered by evil plants that are just messing up with everything. So this is why there are more impact craters here than here. And also it's much easier, much safer to find them in this desert region than the one with a lot of animals that want to, eat you alive or just put some disgusting larvae inside of you. So more people are willing to check out the potential impact sites in desert areas than in the middle of the jungle. So the important thing from my rambling is that the distribution of impact craters is on Earth is definitely not random. However, this is not this is due to the geological processes on Earth, not because the impacts are not happening randomly. So that's important to understand and remember. So here are some examples of impact craters, and this is one that you may be familiar with. I just literally yesterday been digging there. Morasko crater in Poznań. It's the only Polish site where we are sure that the asteroid hit the Earth and made some impact craters. There's like entire group of craters. It's called Strong Field. It's formed when an asteroid that is crossing the atmosphere is disintegrating while atmospheric passage and all the craters are formed at the same time. The largest one is about 100 meters in diameter, and it was formed 5,000 years ago. Slightly larger one, Berenger crater, it's 1.3 kilometers in diameter, and it was formed 50,000 years ago. Another one that is even larger, and also not very far away from us, which is Riss crater in Germany. It's 24 kilometers in diameter. It was made 15 million years ago, and pieces of the, of this area landed even on in Poland. There were relatively recent founds of tektites, which are molten pieces of surface rock that have been melted during the impact and then thrown away on large distances. So large part of Central Europe was affected by this impact. Luckily, it was quite a long time ago. And of course, all of you might have heard about the Chicxulub crater that was formed 65 million years ago and ended up the life of dinosaurs. It is 180 kilometers in diameter. So it's a very largest one, and the largest one that we know of is Vredefort crater in the Republic of South Africa. That is 300 kilometers in diameter, and it was formed 2 billion years ago. It's very easily visible from the orbit. However, it's really highly eroded. There was about 7 kilometers of material have been removed, but still we can see the messed up rocks that were formed during this process. So the crater size, I know that this is extremely basic, but just to be clear, let everyone understand that the crater size is the crater that is created is much larger than an asteroid that created it. It's all because the crater size depends on the amount of kinetic energy that the asteroid is carrying, and obviously the kinetic energy depends not only on the mass, which relates to the size of the asteroid, but more importantly relates to the velocity. And velocities of the asteroids on impact with Earth are really high. The average for Earth is estimated to be about 20 kilometers per second at the entry to the atmosphere. The smaller ones often are like less quick, slightly less quick, but more than 11 kilometers per second. So there's a lot of kinetic energy that needs to go somewhere, but cannot, because that there's Earth in the way, so it has to be released in some way. Here is an example of the numerical modeling that is one of the ways of studying the impact process. So here you have impactor of a size that is supposed to represent the simplified version of a Chicxulub impactor. So the asteroid marked with red here is about 9 kilometers in diameter, and here you can see the target rock, which is Earth in what is today Mexico. So if we run this experiment or the movie, we can see that first of all, just within seconds after the impact, there is something called transient cavity being formed, which is a very deep hole in the ground. In this case, it was more than 20 kilometers in depth, which is a lot, and almost vertical walls. So this kind of stuff cannot be stable, and this is why the crater is being continuing to be formed. The other interesting thing is that the pressures and temperatures at the point of impact, especially for such a large impact, are such gigantic that there is no impactor surviving. Like you cannot find pieces of jigsaw impactor anywhere in the world, at least not yet. And there's good chance that we will never find it, just because all of it is being heated and pressurized to temperatures that are practically turning it into plasma, and then it's mixed up within the rocks, within the crater, and also surroundings. And because of that, we are able to find signal of geochemical signal of increased iridium contents all over the world after the jigsaw impact, but we cannot find the piece of asteroid itself. So if it would be quite small impact crater, this would more or less be it. Of course, the ejecta would just fall down, and the final crater would look like a ball. Those are called simple craters, and if they are small enough so that the strength of the target rock, the strength of the material, can support the size of the hole, that the angles of the rocks forming the slopes of the crater, this stays like that. However, if the crater is larger, the formation continues for some more time. In short, the rocks are not able to support such a large hole, and because of that, it kind of bounces back. You can see that the rocks for a short amount of time behave kind of like a fluid. And as a result, either the central uplift can be formed, which is like a mountain in the middle of the crater, or if the impactor is really large, you can find like a circular mountain ranges. And one of the best examples is Orientale Basin on the surface of the moon, where you have like a couple of I think I see three circular mountain ranges that were formed during this kind of event. So relatively, the craters, the larger craters, are not as deep. However, they are again much wider. Okay, so again, just to repeat what I just said. The crater here, Beringer crater in Arizona, one of the best known examples of craters, was formed by, that is about 1.4 meters in diameter, kilometers in diameter, was formed by an asteroid that was about 50 meters in diameter. This is roughly the scale. Of course, it depends quite a lot on the size estimation, depends quite a lot on how well are we able to estimate the velocity. And those two things are interconnected. So, take the estimations of the size with a grain of salt, because it can very well be formed by a very slow, larger asteroid, or very quick, smaller asteroid. Okay. So what I would like to dive in, that was kind of like an introduction into the basics of impact cratering process. And right now I would like to dive into one issue that interests me the most, which is formation of very small impact craters, and why our impact information about, or the catalog of very small impact craters is so skewed toward one group of impact craters. Okay, so here you can see a plot that is showing the impact rate on Earth. This part of the plot is showing those small bodies that do not leave any impact craters. The impact craters start here with the very small impact craters kind of marked with either the full triangles or diamonds and also those crosses. So here are the impact craters. Here are the observations either at the top of the atmosphere or the different types of camera networks that can estimate the ongoing impact rates for Earth. And what we can see is that there is this kind of mismatch between the impact craters, known impact craters catalog, and the kind of estimate from the other source of data. Small craters are missing from our knowledge, from our understanding. So currently we know 17 craters that are smaller than 200 meters in diameter. And based on those estimations of the recent impact rate, there should be about more than 20 craters that are about 100 meters in diameter in Holocene alone. So Holocene meaning the last 10,000 years. So, time where we should be able to nicely recognize those craters if they exist. However, we know only 5 of those craters. So there is quite a lot of them somewhere, and we don't know where they are. So either our estimations are wrong, and we cannot find, or we cannot find those craters that are there and exist. So what do we know about those 17 craters that are smaller than 200 meters? Here is the catalog. You can see their names here. They are mostly named by the closest town that is located, well, the most near to where they are. This is the maximal diameter of the largest crater. Some of them are like in case of Morasko strong fields. So again, that they were formed by an asteroid that got divided into pieces. But some of the small ones, like for example, White Court, are also like individual pieces. So individual craters formed by an asteroid that did not blow up in the atmosphere. Those are their ages. You can see that the youngest impact crater on Earth was formed in 2007, so not very many years ago. And there is also a very atypical example of the of Douglas that is 280 million years. It's a very strange case, and we are not going to cover that much more. Here is the impactor type, and here you can see also the number of craters in the group. So the impactor type is what interests us. The blue ones are the ones that are iron meteorites. There were iron meteorites found associated with those craters. You can see that most of them are associated with iron meteorites. There are also 2 of them that are associated with the stony iron meteorite, either the palisade or siderite, metasiderite. And there's just one example of a crater that was formed by a stony meteorite. And it's the case that was actually witnessed by people. If it wasn't witnessed, we would probably not recognize it as an impact crater. It's really small. It was about 15 meters in diameter. So it's either that the small impact craters are formed only by iron meteorites, with one exception that was witnessed, or maybe we are really skewed toward finding impact craters that were formed by meteorites, iron meteorites. But how do we recognize that a given hole in the ground is actually made by an asteroid impact, not something else? Here you can see the impact indicators that are used for that. So here are the ones that are marked with orange are kind of important ones. The other ones are just more additional support than anything else. So M goes for the meteorite fragments found associated with the crater, and E is potential pieces of material that was enriched with nickel coming from, assuming, iron meteorite. As H goes for shatter cones, which are a specific way in which a shock wave going through the rock is changing the rock structure. And this is the only indicator that is clearly visible in a hand sample size. The PDFs are another way in which shockwave is messing up rocks in a very, very specific way that we don't understand yet very well. In short, the passage of shockwave through the quartz mineral, quartz crystal, as well as a couple of other minerals, is collapsing the crystal structure along very specific pathways. And you can recognize that in a thin section. You can measure that and show very clearly that yes, this rock was affected by the passage of the shockwave. The only other case in which you can really find that, well, the only other two cases, is either the explosion of the nuclear bomb or the in very, very small amount of material, if lightning strikes the surface, you can also find some planar deformation features. C here goes for coesite, which is a specific type of mineral that is again formed only in a very, very high pressure conditions that are on the surface of the Earth, possible to be produced only by impact of an asteroid. MT goes for melt, so pieces of melted rocks. Again, impact craters can form very high temperatures. OV goes for the overturned sequence, and W for witness. Again, the Carancas crater has been witnessed firsthand, and the Sikhota Alim that was formed in 1947 was, well, kind of witnessed. And the people arrived at the site within 3 days of the event happening. So as you can see, absolutely most of the examples are proven based on the existence of meteorites. And as we discussed, most of them are either iron meteorites or stony iron meteorites. The Douglas case is very atypical. We really don't understand what's going on there. There are also planar deformation features, so it's clearly the impact site, but very, very strange one. And there are also two cases that are not really accepted by everyone as impact craters because there are no pieces of meteorites found within those impact craters. So in general, the impact craters that are accepted by everyone are only those that are either associated with iron meteorites or stony iron meteorites or witness. So why small craters are associated with iron meteorites? What are the reasons for that? First, there is potential that the stony impactors are incapable of forming craters that are smaller or around 100 meters in diameter. And there is some modeling to prove it. The stony meteorites are just weaker than the iron meteorites. So when they are going through the atmosphere, they explode in the atmosphere and deposit most of their energy in the atmosphere. So when they are, or pieces of them are reaching the surface, they are they just land as meteorites and do not form impact craters. Or we are unable to identify small craters made by stony meteorites. And I think that it's probably both, which means that stones are indeed much more weak than iron impactors. However, we are really unable to find those examples. So why do we think it may be a problem? Well, the stony, when we consider the meteorites that we find on the surface of Earth, most of the pieces of meteorites that we find, 96% of cases are stony meteorites, and only 3% are irons. When we consider finds, the irons percentage is increasing significantly to 22%. So the falls are the ones that have been witnessed while falling down. Finds are found later on. It's obviously much easier to find irons than to find stones. This is why their relative percentage increases. And if we consider it by weight, the overall dominance by irons is even higher. So why is that, especially in relation to the craters? Well, first of all, the stony impactors are more fragile, so even if they survive the impact, they would fragment into much smaller pieces. This is the case for the only known case of the crater made by small crater made by stony impactor, which is Carancas. The initial asteroid was probably the size of a small car, and the largest piece of meteorite that was found was about the size of my fist. Most of other pieces were just like sizes of dust grain or sand grain, or maybe small pebbles at best. And obviously it's much harder to find those small pieces of rock and identify them correctly as meteorites than larger pieces of metal that very clearly do not belong there. Yes, I already said that. So second thing is that ordinary chondrites weather very quickly in humid environments. Ordinary chondrites consist of a mixture of rock and some metal, and the metal, when it gets a little bit of water, it oxidizes, and when it oxidizes, it's obviously increasing in volume, which is just expanding and putting the pressure on surrounding rocks and disintegrating the rock pretty quickly. This is why the people that are collecting meteorites are always in battle to stop the moisture from coming into the rocks, because very quickly they can be undistinguishable. And the stony meteorites in general are harder to find because the metal detectors exist and the stone detectors, do not, because there's a lot of stones, or rather stony meteorite detectors do not exist. So this is what I'm trying to explain, is that our way of finding and identifying the craters is very, very skewed toward finding the craters associated with iron meteorites. So there are two types of diagnostic criteria allowing us to recognize impact craters. One, kind of non-diagnostic criteria, a circular form, a circular pattern of the formation, fracturing, the brecciation, so certain types of rocks. There are some anomalies related to gravity, especially in those larger impactors. But all of those properties are shared with other geological features. So for example, the circular form can be often formed by numerous processes related to volcanic processes, related to the processes related to the glacier. So we cannot use that. What we need is diagnostic criteria, which is either the extraterrestrial material or traces of it, like in case of the Chicxulub that killed dinosaurs that were first identified based on the geochemical anomalies very far away from the crater itself, or the shock metamorphic effects such as shatter cones or planar deformation features that I mentioned before. Those are unique for impact craters. They are widespread among different structures and related to the process of deformation. So what I am trying to tell you is that there is another type of process that can be used as to identify small impact craters on Earth that has those like diagnostic criteria in terms of being unique to the impact craters, being widespread and related to the process of formation of the craters. And this is related to kind of environmental effects of those, especially small impact craters. What I'm saying is that there is charcoal that is being found in proximal ejecta of small impact craters. You can see those craters here. There are some that I will mention later on also. Those are all craters that are about 100 meters in diameter. So Ilumetsa here 80 and 50, Kali about 100, Morasko about 100, the largest crater. And in all of those sites within the proximal ejecta blanket, which is material that is thrown out of the crater, there are pieces of charcoal that have been mixed into the ejecta itself. If you go, as I did, through the literature on the impact craters from before, you can find that there are some charcoals being mentioned in other locations, but they were usually just ignored or assumed to be formed before the impact crater and then just intermixed within the ejecta itself. Here is the example of the Campo del Cielo from Argentina. Here is the white card from Canada. In both of those places, those layers with charcoals have been found. So those here you can see that the after going through the literature, those charcoal layers are quite common. They are not present in all of the they were not reported from all of those impact craters, but definitely from a significant number of them. So where those charcoals can be found? First of all, they are present in the kind of ring around the crater, from the rim up to about 0.5 distance from the crater, actually probably slightly less, sorry, not 0.5, 0.1 from the crater. In terms of vertical distribution, they are the most common, very close to the base of the ejecta, although they can be found within the entire stratigraphy. And interestingly, if we have like a double impact craters formed when two asteroids hit very close to each other, you have a double layer of charcoal. Those charcoals have the same age as the independently defined age of the crater. So in case of Kali, this is about 3.5 thousand years. Here you have a date by another researcher that did that based on C14 dating of the oldest organic material within the crater itself. So we know that it has to post-date the crater formation. And here you can see the crater, the charcoal intermixed within the ejecta, and you can see that it gives the same age. The pieces of charcoal itself are really, really small, so they are very easy to overlook. So it's not in most cases, they are very small. So it's not very strange that it was overlooked in the past. Most of them are about 1 millimeter only. So you really have to just be on your knees and just pick this very carefully. However, there are some larger pieces. You can see one here, most probably a piece of larger single piece of branch that have been intermixed as one piece. However, it breaks down into smaller pieces once it's being excavated. So we can say like, well, yeah, charcoal, very normal thing, that there is a lot of charcoal. For me, for example, in this kind of environment, we have a lot of forest fires. They were also present in the past. What's so strange in those charcoals within the proximal ejecta? Well, yes. However, as it turns out, thanks to a lot of research that I did over the last couple of years, you can recognize the charcoal made by the forest fires from the charcoal made by the process related to the impact crater formation. So for example, the temperature, you can measure the temperature or estimate temperature of formation based on the charcoal reflectance. In general, the longer or the higher amount of energy that goes into the piece of wood, that more reflective it is. It also depends on a couple of other things, but the most important variable is the amount of energy. So you can see here the comparison of the same type of rock, of the same type of wood being heated for longer amount of time. Here it has higher reflection than the lower temperature produced charcoal. And based on that, you can recognize, for example, if the charcoal was left by a forest fire that is low intensity, just like at the base of the forest, or it is a very high intensity fire like the one that is going into the grounds, because the charcoal produced by those two processes is very, very different. So when we check the reflectance of those charcoals here, we can see that first of all of those charcoals from very different locations all over Europe, and also couple of other locations that I've checked as well, are very, very similar to each other. And they are also different than they are very similar, and they have lower peak than the usual forest fire. And also that even a single forest fire has much broader range of values than the charcoal from the crater itself. So here you can see here you can see an example of this kind of charcoal from a wildfire that outside can be quite highly reflective here, and inside it is barely charred at all, while all the pieces of charcoal that we find inside the crater are very, very similar to each other. So we can easily recognize which populations of charcoals belong to the wildfires and which belong to the craters. So in order to figure out which process was it formed by, we need to figure out a way that accommodates all those requirements. So it has to be able to produce the charcoals in specific locations within the ejecta blankets. It has to be sometimes present on class, as it was in Cali. It has to be fragmented, not very large. All the charcoals need to have the same C14 ages, and it has to have very uniform reflectance in terms of different craters and also different pieces of charcoals within the craters. So there are two options. Either it can be formed by charring by the radiation from incoming impactor. We know that this kind of thing is happening even during the Chelyabinsk. This was the case, of course, not to very high degree, but it can be. We know it happens. We are not sure if it happens to the degree that is required to start a wildfire in the live and quite wet wood. And there's also other option, which is charring by burying in locally warm ejecta, which also has problems because according to our current understanding of how the impact process works, the ejecta should not be warm enough to form charcoal. So in order to test those two scenarios, I made a series of experiments, which I'm not going to discuss in great detail because we are slowly running out of time and I don't want to bore you to death. But if you are by any chance interested, I will be very, very happy to discuss it for as long as you want, even probably longer than you want. But I will try to stop myself. In short, it's a device for setting up fires in a very, very controlled way. So we can control the amount of energy that goes, amount of energy. You can control the type of atmosphere and a lot of other things, and then very, very in a very controlled way burn stuff. So this is what I did in order to kind of estimate how much what kind of scenario would be required to produce charcoal that has properties that we found in the real life. In short, after a lot of experiments, we are unable to produce charcoal that is uniform in properties, especially within the amounts of time that are realistic for those kinds of very small impact craters. So here you can see the time of heating, and here you can see the heat flux, and the kind of set of images that were also going on this side of the slide that are showing the cross section through the heated piece of wood. And you can see that indeed, quite high heat fluxes can create the amount of some charcoal in amount of couple of seconds. However, those pieces are extremely ununiform, which means that they are very different from what we find in our in impact craters. So this is definitely the properties of grains are non-uniform, and they are very within very unrealistic timescales. So this will definitely not work. However, the second option, charring by burying in locally warm ejecta, again, we run some experiments by first heating the sand to different amount of to different temperatures, including 900 degrees, which is quite dangerous. And when I think about this right now, maybe we should have been thinking more about the safety anyway. And then we just bury the pieces of different type of materials, either fresh or dry pieces of wood inside the heated sand. You can see here the thermocouples and fresh spruce being buried inside to mimic the situation where they are being just covered by the hot ejecta. And then we have again measured the reflectivity, and based on that, the properties of those charcoals are much more are perfectly uniform, or quite perfectly uniform, and also they are overlapping with the with what we can see in the reality of the small impact craters. And based on that, we can conclude that the asteroids forming small impact craters can kill, in this case, trees. At least the bodies of trees have been found. The charcoal is formed, and the properties of the charcoal are consistent within compared number of craters that are about 100 meters in diameter. And the formation mechanism requires prolonged heating for prolonged amount of time, like tens of minutes. More than that is not necessary in order to ensure that the charcoal properties are homogenized within the piece. And it's most consistent with slow roasting in locally hot ejecta. That ejecta initially had about 500, at least locally, had about 550 degrees and then was cooling down. And the impact charcoal, thanks to its unique properties, can be used to identify small impact craters on Earth as long as it killed some plants. So, for example, some impact craters were found on the desert and were formed at Sahara Desert, for example, Camel crater in Egypt. So that would not work, obviously, for that. And this research was in part funded by the Marie Skłodowska-Curie Individual Fellowship at the University of Exeter. So if you right now have any questions, I will be more than happy to answer them.
Thank you very much. Questions? I see there is one question from Neha. Neha, would you like to ask this question on Zoom? Neha, are you there?
Hi, my mic is not that well. If you can read it, it will be nice.
Neha, if you could ask this question yourself. The microphone doesn't work. I couldn't hear this. Okay, we will leave this question to be answered on chat, or I can read it. That's what she said. Okay,
I can see the question in the chat. I can read it and try to answer that. Neha says, just one fun question, hypothesis. If we forget meteorites for a moment, assume there are gas deposits very close to Earth's surface and they combust due to some reason and cause such a crater. How would you reject this hypothesis? So if it's a very small impact craters, well, first of all, it would most probably leave some traces, so that the gas deposits do not just, arrive out of nowhere. If you know enough about the regional geology, if you did your work well, you are able to kind of figure it out. Second of all, it doesn't necessarily looks very similar to that. So there are some cases, more and more common actually, in Siberia. There are those kind of craters that are being formed by this kind of similar process that you just mentioned, by the most probably methane that is being released from below the permafrost that is being melted. So also morphologically, it doesn't look very similar, and it's if you know how it looks like, it's possible to recognize that. Second of all, even if the site is large enough, it should have the signs of the shock wave that is going through the rocks. This kind of process would not produce the shock waves that are able to change the structure of quartz or produce shatter cones and so on. Of course, the problem is that even planar deformation features or shatter cones are not formed at all the impact craters, even if there definitely was the shock wave going through the rocks. Because, for example, you can have asteroid hitting some basaltic rocks that do not have quartz there, or other numerous enough minerals that have easily recognizable planar deformation features. The impactor can hit some granitic rocks that do not form easily recognizable shatter cones. There are some shatter cones, but not so obvious. So, in geology, unfortunately, the problem is that we rarely get final answers. We are just able to get as close to the answer as it's possible at a given moment.
Okay, thank you. I think it applies.
Your question.
Applies also to us. Paweł, you have a question?
Yes, hi, hello. Very nice talk, very nice project. And I have some general question about your first animation presented today. I mean the impact perpendicular to the surface of the Earth. So could you explain, could you say more about different angles and what will be different? I mean the depth of the crater, or maybe also the shape of the crater, maybe something else.
Yeah.
So I assume that I understand that you assume the 90 degrees angle between the surface and the direction of the impactor, right?
Yeah, this was the right angle. Yes, most of the numerical models, at least until recently, well, still are made based on this right angle, just because of the computational costs of those kind of research. It's done in quarter space or 1/8, and then it's just symmetrically reproduced. So actually the part that was actually calculated is like half of it. So this is why most of the numerical models you will see are done in this way. However, right now with the increasing computational speed of available computers, are more and more different angles are possible to be modeled. And so first of all, you can notice on the surface of Moon or Mars that most of the impact craters are round. They are not elongated as you would, because obviously you get very different angles, and this is of impact, with average being 45 degrees, let's say. However, only if you have very low impact angles, you get the distortion in shape of the crater itself. So for example, it has to be below 15 degrees in order to have the crater being more elliptic, and it needs to be really, really low in order to be like really elliptic. However, the the angles of the impact is much more visible in the shape of the ejecta blanket, if it's preserved, and often at the other planetary bodies that do not have the amount of geological processes happening on Earth, you can actually see that. So for example, you can see that the shape of the ejecta, if the angle is, for example, about 30 degrees, the shape of the ejecta is kind of like a butterfly shape that is not, the material is not just thrown out symmetrically all over the crater, but you have like a zone where the ejecta is almost not present, and this is the zone from which the impactor came at a slightly at 30 degrees or lower. So you can see that. Second of all, there are things that I mentioned before called tektites, which are the kind of very distal parts of the ejected material that have been melted, like totally melted. So it's impacted glass. And they also require a very specific angle of impact. Only then they can be, this melted rock can be ejected at those great distances. So again, there are some markers that we can determine about the angle of the impact and the direction of the impact. However, in many cases, and I would say in most cases, this is impossible to say, because in most cases you just get like an impact and then release of a large amount of energy at a point of touchdown, and then it's pretty symmetrical.
Okay, I see. Thank you very much. Very nice.
Okay, thank you. Are there any questions here from the lecture room? Maya.
Hello, thank you for the nice talk. And I have a question about the Carancas impact site.
Yes.
Of course, apart from the impactor being rocky, did it have any distinctive differences, the crater itself, from the iron ones?
Crater, no. Again, this is the entire thing that counts for the crater creation, for the, let's say, morphology of the crater once it's being formed, is the amount of energy that is being released at the point. So it's exactly the same thing. The Carancas is very atypical example because, well, first of all, it's the only stony one, but it's also really small. It's only about 15 meters, and it was possible, like, if it wouldn't happen in Peru, that the impactor would disintegrate in the atmosphere. It's just because it happened to hit the Earth that was sticking out at 5 kilometers above the ground. It managed to, in more or less coherent one piece, hit the Earth. So in terms of that, it was atypical, very atypical. I'm not sure if that answers your question. The form of the crater itself, you would not be able to recognize if the given hole in the ground was made by an impactor made of iron or stony impactors. Yes, especially that we have only one example of the other one. So,
Okay, thank you. That was my question exactly.
Okay, thank you. I will use the opportunity to ask you one more question. If you were able to go to the moon yourself with your shovel, where would you go and which crater would you study and what could you learn from that?
Just one? I think, well, actually, this was a topic, this exactly question was a topic of my, one of the best experiences of my life, which was internships at the Lunar Planetary Institute. By the way, if there are any students listening to that, it's still open, the application, so you can still apply. Just Google Lunar and Planetary Science Internship, Lunar and Planetary Institute internship. Amazing thing. And the question, yes, was where to go. The answer is there's not just one impact site, I think. One of the very important places is Copernicus crater, just because a lot of the chronology of the entire solar system is dependent on that. So I'm not sure if you are familiar with the crater counting method. It's generally based on research done during the Apollo era, and this is how we know that, for example, the recent this is how we know where to send the rovers to the moon to check out when some of the youngest lavas were, erupted, because we count the number of craters and the sizes of craters that we see on the moon, and then we are able to kind of back calculate that to the rate using the rate of impacting of the surface. And figure out what was the age of the crater. So, for example, 30 craters of this size mean, 1 billion years, let's say, for example. But all of that is kind of based on a couple of samples that have been collected by the Apollo era astronauts, mostly from the basalts that are about slightly older than 3 billion years. And they entire younger part of the ray is anchored by this not very well defined age of the Copernicus crater. So I would go there, because this is not important only to determine the ages of all the things that we see on the moon, but also all the things that we see on the entire other stiff part of solar systems. So that's my answer. If
Excellent.
I just have one.
Sure. Thank you very much. Thank you for this very entertaining and enlightening talk. So let's thank our speaker again.
And if you have any questions later on, or or have any suggestions for me that can be useful in my studies, or I can help with any geological way of thinking about asteroids, just let me know. I'll be happy to discuss.
Okay, thank you very much. So we stop here, and there is going to be a seminar next week, even though it's Friday, but it's going to be Tuesday in the calendar, but in the for students it's Friday. But the seminar will still happen usual time, usual day. So see you next week.